Hello, everybody. I hope you must be listening to my previous lectures. If you have suggestions, comments, or questions which are bothering you right now, so I suggest you to please mark them up, note down somewhere, and so that when we meet next time, we can discuss them in a bit of detail. And I will try to uh, solve your curiosity, so to say. Today, we will discuss about descriptive statistics, some of the mathematical tools we will learn about descriptive statistics, and some graphical methods as well, which are most common. And I suppose everybody who is working with quantitative analysis should at least be familiar with those methods. So we continue. I will start this lecture again with a quotation. It's a famous saying by an American writer, and it says, torture numbers and they will confess to anything. Actually, this is what the statisticians or quantitative analysts do. We get numbers in terms of time series or in terms of vector, so to say, and we try whatever possibilities we can to explore patterns in the data. We implement graphical methods, a basic graphical methods, as I said before. Once you have a data, try starting with some graphical methods. See if you can observe any pattern in the data, and then go for some mathematical methods, statistical models, or descriptive statistics, whatever ways you have in your capacity to implement on that data and then learn more about that, explore. But start with graphical methods. So that's what we do. We torture numbers or data or series in many different ways just to observe patterns in the data, just to listen, just to hear about what the data says actually. So in terms of descriptive statistics, basic numerical methods for exploration of data, well, we start with measure of central tendency. And by measure of central tendency means, in general, you can say the mean, the average, the where the center lies of the data. So if you have a data spreaded in, so actually this mean lets you know about the spread also, so to say, how far values are deviating from mean, where the mean is located for that particular data. So we start with measure of central tendency. We evaluate means, or say averages, and there are three different ways actually to calculate averages. So given a sample of measurements, say x1 up to xn, well, this is a mathematical notation, and x1 to xn means a set of data ranging from first value to nth value. And n is the sample size of the data, and xi is the value of the ith observation. So as I said, there are three common ways to compute central tendency. The first one is arithmetic mean. So in the arithmetic mean, I hope you are familiar with this formula. We just summed up together all the values, we add them, all the values together, and then we divide the total sum by the number of observation, by the total number of observation, which is n here in this case. So if you look at the examples, a very basic example over here, let x equals to the age of a randomly selected student sample, and these are the ages like 20, 25, 30, 35, 40, 45, and 50. Right? So there are 7 students in a group, and their ages differ. Each student has a different age, and it ranges from 20 to 50. So if somebody asks me to evaluate the mean age of this class group, so what I will do, I will add all those numbers together, which is the sum is actually 245 in this case, and then I divide that number by this number of observation, which is 7. So the average age of this small group of students is 35. X bar, we usually use the notation X bar for representing sample mean or arithmetic mean. The problem with this measure is that it is sensitive to extreme values. So if you have a single value, say 70 or 80, if that value comes up into that example, the whole mean would be shifted to that particular value. So that's why extreme values, they attract, well, better to say they push the mean value to themselves. This is the problem with arithmetic mean. And that's why arithmetic mean is not always a good measure of central tendency. And we have some more measures. So we go ahead and we learn some other methods like sample median. So the median of a sample data is the middle number when the measurements are arranged in ascending order. So if you have a data, you arrange them in ascending order and then you pick the middle value, whatever that middle value is. So that middle value will give you the median of the data. So now if n, the number of observation, is odd, then the median is the middle number. Well, if you say n is 5, then median is what? N plus 1 over 2th number. This shows the position of the number, which is the median of your data. So if you have n equals to 5, then 5 plus 1 over 2 is 3. So the third value in your sequence, when you arrange them in ascending order, that third value will be the median of your data. And if n is even, so you take the median of two middle values. So you take the average of two middle values and that value will give you the median, right? So just recall, if you have n is an odd number, if the number of sample is an odd number, you arrange them and you pick the middle number, because when n is odd, then there is only one middle number, right? But if n is even, then there are two middle numbers, so to say. So you take the average of those two middle numbers, and then that average value will give you the position of that. So median, actually, the position of that value will give you the median of that sequence. Say an example here, example number 1, you have sample for 5 observations, 9, 2, 7, 11, and 14. So first we will arrange them in ascending order. So we get the answer 2, 7, 9, 11, and 14. And if you arranged it, then you notice that the middle number is only 9 over here. So that 9 is the median. Similarly, if you have samples of 6 values, so to say 9, 2, 7, 11, 6, and 14, you have 6 observations in the sample. So you arrange them in middle order, in ascending order, So it's 2, 6, 9, 7, 11, 14. And then you take the average of two middle numbers, which are 7 and 9, right? So the 7 and 9, the answer is 8. So 8 is the median of that particular number. Notice that the median is insensitive to extreme values, because median is a measure of location or position. So median gives you the position or the location of the number, doesn't give you the number actually. And that's why median is more popular when you are looking for or when you have data with extreme values. Mean is not that suitable when you have extreme values or outliers. Sometimes we call in statistics those values as outliers. In some graphs, hopefully we will see those outliers. Graphical ways are also very good ways to somehow judge are there any outliers in the data or not. The third measure is sample mode, and the mode is the value of x. X means the set of observation that occurs with the greatest frequency. If you have data and in this particular data a particular number is occurring many times, so that particular number is actually the mod of the data, because it occurs often, it occurs very frequently in a sequence. Consider a sample here, 2, 9, 7, 11, 7, 2, 4, 7. It's obvious that one number which is occurring again and again in this sequence, in this small sequence, is number 7. So the mod of that particular data is 7. So these are the three measures of central tendency and we will be working with those measures if we come across with some data in future. So measures of variability or dispersion. So we move on. We have noticed or we have learned about how to calculate the central value of a data. Now we are mainly interested in how big is the spread of the data from that central value. So we have a central value. Now we want to know, do we have a huge dispersion in our data or do we have a small dispersion in our sequence? And that's what we can notice through some measure of dispersion, some measure of variability. So the first of the basic and the first measure in this setting of measure of dispersion is range. And range is nothing but the difference between maximum and minimum value. So if you have a sequence of observation, like here, 2, 9, 7, 11, 7, 2, 4, 7. So what you will notice, you will observe, you will just point out the maximum value in this sequence and the minimum value in this sequence and just take the difference of those two values. So in this sequence, the maximum value was 11 and the smallest value was, or the minimum value was 2. So the range or the difference between those two numbers is actually 9. So this is the measure of dispersion for that particular sequence. Well, measure of dispersion, of course, has a very important meaning in statistical analysis, but range is not a suitable candidate to measure that particular variable, that particular parameter actually. So we move on to some more methods. For instance, mean absolute difference. This is another measure of measure of dispersion actually. So what we do here, we subtract each value, x means each value, from its mean, and we take the modulus. And why we take the modulus? Because we are only interested in positive values, not in the negative values. And then we summed up together this difference, all the differences from the mean, and then divide by the number of observation. So this measure will give us MAD for that data, the mean absolute difference. And for this particular data, you can evaluate immediately. So first you have to evaluate the mean of that data, that sequence, a small sequence, and then start subtracting each value from the mean and take the modulus so that you come up with positive values or positive differences in the end. Add all those differences together and then divide by the number of observation. The third measure is sample variance, which is very popular actually in statistical analysis. And in sample variance, well, sample variance is not that different from the mean absolute difference. The only difference is we take the square of the values. We don't take modulus to make them positive, rather we take the square. So that's why we call this sample variance as the squared difference from the mean. So we subtract each value from the mean, we squared them together, and then in the end we summed up together all of them. Finally, once we have summed up together all those differences, or squared differences actually, we divide by the number of observation minus 1. And if you are interested in, we can discuss later why we subtract here by n minus 1. Why not by n actually? So sample variance is absolutely simple. As I said, again we just take the squared difference from the mean of each observation and then summed up together and divide by the number of observation minus 1. Sample standard deviation is another simple measure of deviation actually, and it's even simpler to calculate because once you have calculated mean, the mean difference, or in another word, the squared mean differences, you just take the square root of those differences and then calculate this sample standard deviation. Notice that variance, if you take the square root of variance, this will give you the standard deviation actually, the sample standard deviation. So these are the four measures for measure of dispersion of variability. I would like you to practice with this particular data and evaluate all of these measures. If you come across any problem, note it down, and next time when we meet, we will discuss in detail. Measures for finite population. So far we have been discussing about samples when we have a sampled data. Remember the difference between sample and population in our previous lectures? So usually we use the terminology of capital N to denote the population size and small n to denote the sample size. And again, like x is the data again, but x goes from 1 to x capital N. It means it covers all the population. The population mean is absolutely the same. You summed up all the values and then you divide by the number of observation, which is capital N. The population variance is exactly the same as we noticed before in our previous slide, with only a slight difference. And the difference is, so first you take the difference of all the values from the mean, you squared them together, you summed up all the differences, but here you divide them by the total sample size. You do not subtract -1 as we did in a sample case. And again, population standard deviation is nothing but the square root of the population variance. Here are some notations. Sample statistics, well, we call statistic means every measure evaluated or calculated through samples. We specify them as a statistic. And these are like X bar for mean, S square for variance, and S for standard deviation. For population, we use the terminology of parameter. And for parameter, we have mean notified as mu, variance as sigma square, and standard deviation as sigma, right? So we have come across with some basic notations for population and samples, and also for measures of central tendency and measure of dispersion or variability. Now we move on to a more interesting, somehow very useful in some graphical structure also. This measure is very known and very useful in many ways actually, and that is called percentiles. So calculating percentiles is useful if data is badly skewed. Well, skewed means if you have uneven data with respect to the central value. For instance, you have a data where the values or the observations below central values are less than observations above central values, or vice versa. So we call them as skewed data sets. And when we have a skewed data set, then we should go for percentiles. Then mean is not a good measure, right? So if, let's say, x1 up to xn be the set of observation arranged in increasing order, we have already arranged them in ascending order or in increasing order. Definition of that particular measure, the percentile measure, is this: let p, which is the percentile between 0 and 100. The pth percentile is a number. Well, it is a number, any number. We call them y. Is a number y such that the p percentage of all the measurements fall below the pth percentile and 100 minus p percentile fall above that. So this p will give us a kind of target, so to say. So below, we say that below that percentile we have pth percentage of the data, and above 100 minus p, because 100 is a total range or total area of that particular percentile measure. So we subtract that p from 100, and then the rest falls above that region. So we come across, let's have some examples so that we understand this measure more closely. So we have an example here with observations of 2, 5, 8, 10, 11, 14, 17, and 20. And somebody asked me to evaluate the 30th percentile of the data. How can I do that? Well, first of all, I will calculate how many observations I have in this data. Well, I have 8 observations in this data, and then all of them are arranged in ascending order. If they are not, then I have to arrange them first. And now I will calculate the position. So find the position of that percentile, the 30th percentile. So the formula is pretty simple. I multiply with the percentile I am interested in times n plus 1. N plus 1 is the number of observation plus 1, which is in my case is 2.7th value. 0.3 times 9, which is 2.7th value. So that value is the 30th percentile of that data. Now the question is, how can I evaluate that value? So you see 2.7th value ranges between second and third value, right? So now we will work out. So we say, well, 2.7th value is bigger than the 2th value or the second value. So we say second value plus. How much it is bigger? Well, 0.7 is the proportion, because that value or that position is bigger than the second value by 0.7th points or 0.7th units, so to say. So we multiply 0.7 by the difference between third and second value, because this 2.7 lies between third and second value. Now plug in all the values. So second value was 5, 0.7 is constant, third value was 8, and again second value was 5. So the answer is 7.1. So the percentile of that particular data is 7.1. So pretty simple actually. So we just multiply the number of observation plus 1 times the percentile, the p, which we are interested in, to calculate the position of that value. And once we are done, we evaluate the position in another manner. Special cases, well, sometimes we are interested in lower quartile. We call them lower quartile because it's a quartered value, so to say. In another words, 25th percentile. We denote them by Q1, median Q2, which is the 50th percentile, the middle value, and upper quartile, which is Q3, is the 75th percentile, right? So these are the three measures which we use a lot in some graphical representations as well, and you will see soon how they can be used and how much they are important for many analysis, for many perspective of data actually. Interquartile or interquartile range is also very important, and this interquartile range is nothing but the difference between the third quartile and the first quartile. So we calculate those two values and then we calculate the interquartile range. Those measures are very useful in making the box plot. So in the next lecture, you will hear about graphical representations, and then you will see how this slide can be utilized over there. Thank you very much.